Alrighty guys, so quick reviews of diagrams because as you probably noticed the past 2 weeks we've had a lot of diagrams kind of come into view and you should be comfortable identifying kind of what you should be able to determine from those. Will, what does a phase diagram look like?
It's like, so you go like that, and then one line curve up, and then halfway on the line it's another curve line.
Like that, okay, and then what are the axes?
I don't know about that.
Syrian?
Is it temperature on the left?
Temperature down here, and anybody? Pressure, right, this is the pressure one. This is the pressure versus temperature information, and from the phases that we can determine, who can tell me what each of these little segments are supposed to represent? Syrian.
The first one's solid, the second one's
Great, so we can see all the phases of a particular compound, like I can say water is my compound here, and for every pressure, I can see with the temperature at which it melts, at which it freezes, at which it condenses, sublimes, deposits, and vaporizes. I can see all the phase changes present basically here. So if I say I'm going between solid and liquid right here, that's the temperature. I would say that's the temperature at which it what? Melts. Okay, solid to liquid is melting at that pressure, whatever that pressure is. I could say from solid to gas, that's the point at which it sublimes at that temperature at that pressure. I could also say this is the boiling point because I'm going from liquid to gas, and that's the temperature at which it boils at that pressure. So I can see a variety of things, but it's all about phase changes. All about phase changes. We don't really do any calculations with that. We only look at the graphs.
Good morning, students that are taking the human geography test. Please go to the test location at this time. Students taking the human geography test.
So we only look at the specific pressure. We determine what temperature it boils, freezes, and all those other phase changes that could occur. Great job, guys. All right, so next, Frank, what does a heat curve look like?
It's yeah, your axes, and then like a ladder, like stairs.
Stairs, okay, and so each of these actually represent phases as well, right? So solid, liquid, gas. What are the axes?
Left one,
This is temperature in degrees Celsius, right? And
that one.
what has to be added to cause these changes to occur? No, what has to be added to the compounds to make them relates to kinetic energy, kind of. Anybody picking up what I'm putting down? Heat, thank you. You can add heat energy. So as you add heat energy, the temperature can begin to change, and as we change, we occasionally will change phases. So along the horizontal, the slanted lines there, this is going to use what equation if we have to do a calculation with it? I want to figure out how much heat was used to make that happen. MCAT one, right? Q is equal to MCAT, so I could actually determine the energy it took, so heat energy it took to change the temperature by whatever the degrees Celsius that was. Otherwise, I have another section in the graph, the phase changes, and what equation just goes along with phase changes. Yes, you're in. Say it again. So I'm going to use mass times delta H fusion, or maybe delta H vaporization. It doesn't have to be mass, though it could be moles. So just make sure you're looking at the delta H's to see what units they give you, and then you move on from there to determine your heat, your Q. All right, so you remembering some of this? A little bit? Okay, Brandon, what's a cool curve look like? So where do I start? So gas, liquid, solid, right? So it's completely opposite, but what would I call the transition right here? I wouldn't call it vaporization because that's what this one was. What would I call this one? So fusion is actually, this is delta H of fusion, and this is delta H vaporization. Just seeing what we can pick up, okay? So this is delta H condensation, right? So it's the opposite of vaporization. Same number, different sign. We're releasing energy versus taking in energy. And then Brandon, last one over here. Delta H freezing, which is the opposite of melting, aka fusion, right? So there's the same numbers but different signs, releasing versus absorbing energy. Wonderful. Okay, so same story. We're basically there. Raise your hand if you can tell me what a reaction coordinate or a reaction diagram looks like. Isabella, what you got?
I can figure it out.
Okay. Anybody else? Irie?
The y-axis I mean, the x-axis
Yeah, this is still temperature and heat. Yep. So I'll start. Okay, so it's got a little axes. Yeah, Mikado?
I don't know. I feel like I'm like right. It's right on the tip of my tongue. Like if I say it, it's gonna sound loose.
Just say it.
It's like like it's like a point, right? The graph.
It's got a point.
And that point is like indicating.
What's it? Draw it in the air. What's it look like?
See, I can't.
So it goes like this and it goes up. Okay.
Oh yeah. See?
Thank you, Mika. I was looking for a jump start here. Okay. So that jump start actually has the point that you're looking for, or it can go down. So there's two of them, right? So what do you call the one that starts low and ends kind of high?
So,
Endothermic. Took in energy versus the one that starts kind of high and goes low. Exothermic is releasing energy. So I'm going to draw two of these, okay? So one that goes like this, I'm going to end kind of high. So your reactants are here, your products are here. This over here would be potential energy changes, and this is like the reaction progress, or time is another way to say that. So over the course of this reaction, you have two things that are important on these graphs. From the reactants to the tippy top, that's the energy it takes to activate the reaction. What do you call that? The energy it takes to activate the reaction.
Isn't it activation?
Activation energy. It's not a secret. It's very similar to the definition. So we label that EA, activation energy, energy of activation. So that's the point from the reactants to the tippy top, which is the activated complex. Okay, that's what's called the activated complex. Now, the other point of the difference of the energies of the reactants to the products, that's not this green part, right? That's going to be the shorter distance between the reactants and the products, which is from here to about here, right? That's the energy difference. That's the thermal energy difference between the reactants energy and the products energy. What can we label that? Delta. It's the thermal energy difference, heat energy difference. Delta H, enthalpy. Another way of saying that is heat of reaction or enthalpy of reaction. Or this is the amount of energy that was put into the process. That's the positive endothermic nature of that graph. Okay, that's showing you it's endothermic. The heat energy is higher in the products than it was in the reactants. So similar but different. How would I draw an exothermic curve? Start off high, still have the hump, and drop low. So where's my activation energy? To the top of the curve still. So your reactants start here. Your activation energy is from where the reactants are to the tippy top. That's EA, activation energy, energy of activation. Still potential energy and reaction progress here. But where do you see a release of energy? Where do you see the delta H that's negative? To where the products end, right? So if products end down here, reactants to products is about EA big, right? About from where the reactants to where the products final are. And that's going to be a delta H of negative. It's releasing energy from that standpoint. Okay, last one. What does a solubility curve look like? Mikado.
So it's like it has a lot of lines.
A lot of lines. Like, what do they look like?
Some are curved. Like it's like I guess it depends like what elements. It are.
What compounds? Mm-hmm.
Yeah. Compounds. So like you can have like one curve going like this, or like one curve going like this.
Like this. Okay.
And one curve could go down.
Which likely would this one be? What kind of substance?
Gas.
Thank you, Mikado.
Oh, I'm sorry.
What kind of substance? A solid or gas? That's exactly the sound they make. Nope, the gases. There you go. Okay. Trying to help you out there. Okay, so these are, like, this could be potassium nitrate, and this could be sodium chloride, but you've got a number of different lines that kind of intersect each other, but what this is telling you is how soluble things are at what axes. Like, what kind of information is this? What's on the Y? On the Y? No, temperature's down here. Okay, this is in degrees Celsius. And then this would be grams of solute per something about the solvent. I'm going to tell you, it's 100 grams. 100 grams of solvent. So basically it's saying how many grams of solute can dissolve in 100 grams of solute, or solvent. So potassium nitrate's pretty dang soluble. You can see that it's going to have kind of an exponential increase in solubility. Sodium chloride's kind of stable. Gases in general, when they get heated up, right, temperature, heating up, what happens to them? They get what? They get less soluble, and that's because of their increased kinetic energy, which means that they can like pop out of the solution, escape to the top of the solution very easily, where solids are not as likely to do that. Now, with a curve like this, I could ask you 3 different questions. I could ask you, is this solution saturated, unsaturated, and supersaturated? And kind of what are you looking for when you hear those words? Above the line, on the line, or below the line. So if I said, you know, at 20 degrees Celsius, I put in 80 grams of potassium nitrate, what kind of solution have I made? 80 grams, let's call it up here. Say again? Supersaturated, because it's above the line of saturation. At 20 degrees Celsius, let's say this is like 50 grams of potassium nitrate. So 50 grams would be a saturated solution. If I put in 80, 30 grams would precipitate out or crystallize because it's supersaturated. But what if I put 20 grams in? Unsaturated. And how much more could I add to make it saturated? 30. And so you're really looking at a specific temperature and kind of looking at the graph of the solubility saturation point, which are all the points of green right here. And then you can read the graph on the left-hand side to look for the grams given. So that's our solubility, and I have some good links for that on the website. Okay, so really I think you guys are fine on calculations. It's just remembering what graph is kind of telling you different pieces of information and identifying the main points on those graphs. Okay, so if you guys have your problem set, PS set 15, 16, that goes on your desk, 1 through 8 on your desk. Rainbow Lab, who's yet to finish that? There's like some analysis questions you guys need to finish. Okay, the lab will only take us about 45 minutes, 50 minutes, so I just want to make sure that you guys have some time beforehand. So I'm going to make you guys watch first a quick video on ice cream, and then you guys can make sure that you address some of these things before you get to the lab. I need to check some of those, so don't put those away at all yet. On Monday, you have a cumulative test, which is gases, thermo, and solution. So you should have your gas flowable, you should have your thermo flowable. If I have not checked your thermo-chem flowable, I need to check it quickly and then I'll give it back to you because it's a nice study aid. Okay? And it won't be that long because afterwards we'll start taking some acids and bases. Yeah. You can get the data from somebody else, that's fine, because everybody still has their labs covered like 5 people. Okay? Alright, so let's do a quick watch of a video. Let's do this from here. Oops, I accidentally have them. So Adele gets us moving in the morning.
Welcome to summer. The sun is shining, it's hot out, and you have the beach on your mind. And we know just what you're craving to cool off. Ice cream.
We don't need to watch those.
This delicious treat comes in many different flavors and forms. Hard ice cream, soft serve, custards, and sherbets. But have you ever thought about how these varieties are created? Well, we talked with American University's Matt Hardens. Turns out the ice crystals in ice cream determine the consistency.
What you're doing when you make creamy ice cream is you control the size of ice crystals in your ice cream. So we're going to start off with this hexagonal shape for a growing ice crystal. As you go along, you add more and more ice to the outside of your growing crystal. Eventually, we get really large ice crystals.
So the bigger the crystal gets, the harder and crunchier your ice cream gets. If you don't want to crunch on your summer treat, you want your ice crystals to be small. But how do you do that? There are 2 ways. First, put an emulsifier in it. Ice cream is a mixture of water and fats. These 2 substances naturally want to separate. If they separate, like middle school kids at a dance, the water molecules will hang out by themselves on one side and will be more likely to form large crystals upon freezing due to their interactions. An emulsifier keeps the water molecules and fats mixed together, which keeps the water molecules away from each other, allowing for smaller ice crystals to form. The second way to control ice crystal formation is by changing how fast the water freezes.
If you freeze your ice crystals very quickly, very rapidly, right, you get lots of little tiny crystals like this. If you let them freeze over a long period of time, you get bigger and bigger crystals.
Proof that it's not just all sweet talk. Matt made ice cream 3 different ways. First, we made ice cream the old-fashioned way, in an ice cream maker.
So what this does is there is a heat exchanger in the middle, so we get this really cold in the freezer, and this needs to freeze use over the course of a day, maybe 2 days, to get all the liquid inside of this container really cold. And what will happen is this will turn and churn our ice cream as it freezes. And this will take about a half an hour. So obviously this is a long time. And so our ice crystals out of this preparation are going to be a little bit bigger than some of our other preparations. Another way to cool down our ice cream base is to use salt and ice. And the salt changes the freezing point of the water, and so we can get lower temperatures with this bag of ice, right? With salt. Now we're going to play with liquid nitrogen. So what we want to do is pour slowly while we mix it up. So I'm mixing like I did in the dry ice for two reasons. One is whenever you make ice cream, you want to keep incorporating air into your ice cream. That helps with the flavor and the stability of your ice cream. But also because we want to quickly transfer the liquid nitrogen through our liquid to cool it evenly.
Sugar and fats play a crazy important role in the flavor of ice cream. Cold tends to numb the taste buds, so consuming ice cream dulls the sensitivity of the tongue. This is why ice cream has so much sugar in it. Try tasting melted ice cream and cold ice cream. The melted ice cream will taste significantly sweeter. As far as the fat goes, unless the ice cream's label is light, low fat, or non-fat, ice cream must contain at least 10% fat per milk. Premium ice cream, no, the really good stuff, has up to 20% fat, which gives it a velvety, rich texture. So, we tasted the results, and that was right. The salt and ice cream was crunchiest. The ice cream maker ice cream was less crunchy, and the liquid nitrogen ice cream was incredibly creamy. Now, we're not saying you have to buy liquid nitrogen and start blasting your ice cream with it, but at least you now know why your ice cream sheet is so silky smooth. Hey, if you like learning cool things like this, make sure to hit that subscribe button. And while you're here, check out why bakers are so delicious, or how artificial Skittles taste. The more ice cream you have, check out the summer.
Walking through the idea of making ice cream as a freezing point depression lab because the salt is involved in depressing the freezing point. Okay. So other than that, I'm gonna go ahead and let my folks who are done, all the way done, have no missing work. Go ahead and back to the lab. Everything's acting for you. I just want to make sure I pour the milk because I don't want to have to cry refill milk. Otherwise, if you have some work to do, then sit here for a little while and then quickly get done so you can go back and make ice cream. So I should see bodies moving. Leave your desk for heating.
Right on mine.
Coming back here. If you have your work for me, leave it on your desk and I'm going to come and check it while you're ready to make ice cream. Back here you have your ingredients, salt, sugar, vanilla, spoons, you have everything else you need.
I did that.
Sorry, I haven't been to the lab.
I got it.
And the lab I'll put right here if you need to finish something from that. It shouldn't hopefully take you very long.